For the rest of class today, I'd like to do a problem or two from section 4.4. I've given you some problems on this already about families of functions and modeling. That will help us indeed for Wednesday's class when we talk about the project. And we're skipping section 4.5. We'll go back and also look at some problems related to, well, related rates is what it's called. Gave you a couple problems about that for today. So we'll do some more problems on that. And that's probably the main thing we'll have time for. The first problem I'd like to look at in section 4.4, I believe I assigned to you for today's homework. Tell me if I'm wrong. It was one of these questions, number 33 or 34. I don't remember which one of those I assigned. I think it was one of them. I'd like to look at number 34. And we'll go ahead and solve the question, but I'd like to do a little bit more in talking about this. These kinds of curves here, or curves related to these curves, are very important in math and its applications. If you've taken AP statistics, you would remember something called the normal curve, a normal distribution. These are very much related to normal curves. Bell-shaped curves is another name for them. So the formula here, section 4.4, number 34, it's a family of curves. It's not just one curve. A and B can be anything. A family of functions or a family of curves. E to the negative x minus a quantity squared over b. And by the way, this negative sign here is outside the squaring. You do the squaring first, then divide by b, and then put the negative sign. So no matter what x is, you're really raising e to a negative power here. I mean, well, if x equals a, then it's the zero power, but it's never a positive power. That negative sign does not go away because of the squaring. It's not being squared. Okay. B is positive here, but a can be anything. Let me give this function a name, even though the book doesn't do that. Let me call it f with a couple subscripts. I'm going to use subscripts here. F sub a comma b of x. Why am I doing that? For one thing, I'm doing the subscript just to emphasize that this is a family of functions, one function for any fixed values of a and b. But different values of a and b give you different functions and different graphs. So it may be good to emphasize that here by doing something like this. And in fact, if you want to program Mathematica to make these graphs and allow a and b to change, you do need to use subscripts in a way that I'll show you. Let's just, instead of doing what the problem says to do, let's just do a little exploration. What does the graph of this function look like for different values of a and b? That's what I want to explore here. Well, the derivatives, first and second derivatives, are tools that can help us understand the graph. Take the derivative here, set the derivative equal to 0. I'm going to solve for critical points and possible local maxima or minima. I need the chain rule here. If this were just an x, the answer would be e to the x, but hey, it's not an x, it's this entire thing. So I raise e to that inside function, then multiply times the derivative of the inside function, the derivative of this entire thing. Kind of tricky looking. You don't have to expand this out, just leave it as is. Bring the 2 down in front with a negative sign, negative 2 x minus a to the first power divided by b. The b is just a constant divisor. It just stays there. And then if you use the chain rule again to differentiate x minus a, you get an extra factor of 1, which of course doesn't need to be written, but I'm writing it to emphasize that's the derivative of x minus a. So I really use the chain rule twice in doing that. This can be simplified a little bit. bring the -2, say, and the x minus a out in front. And you can write that. If I set this equal to 0 to try to find critical points, there's only one way this product can be 0. -2 is not 0. E to a power is never ever 0. So the only way this whole thing can be 0 is if x minus a is 0. This implies x minus a is 0, which implies x equals a is the only critical point. I've been telling you this is a bell-shaped curve. The graph of this looks about like this. In fact, so that's going to mean there's going to be a maximum at a. In fact, this derivative does change sign from, careful here, positive when x is less than a and negative when x is bigger than a. Why? If x is, the e here is positive, first of all. If x is less than a, x minus a would be negative, right? Pretend a is 5. If x is less than 5, like 4, 4 minus 5 is negative. And -2 is negative. So you have a negative times a positive is a positive. F prime is positive when x is less than a. We could make a number line here. F prime is positive when x is less than a and negative when x is bigger than a. That means f itself is increasing when x is less than a and decreasing when x is greater than a. Just making an upward arrow when f increases and a downward arrow when f decreases. That would be consistent with a bell-shaped curve looking about like that. It will not only be a local max at x equals a, it will actually be a global max. What about the second derivative? And why take the second derivative? Well, we can find inflection points for one thing. We could also confirm we got a local max at x equals a. Differentiate this entire thing. Oh, I'm going to need the product rule as well. Let's see. Differentiate, think of this as the first function. Differentiate that, you'll get a -2, right? Because if you multiply the -2 through here, you get -2x plus 2a, and a is a constant. The derivative of that will be -2 times the second function plus the first function times the derivative of the second. Hey, the derivative of the second here is the same as the derivative of the original function. So I'm just going to get another factor of -2 times x minus a. And -2 times x minus a quantity squared would be plus 4 times x minus a squared. So I just did a couple steps there in my head. I'll say it again. Right here, what I did essentially is I wrote this for, I imagined writing this first function, -2 times x minus a, then differentiating the second function from the product rule. But that second function is the same as the original function. So its derivative is the same. The derivative is this entire thing. So I really have -2 times x minus a times this entire thing, which means I have two factors of -2 times x minus a. I'm squaring -2 times x minus a, so I get positive 4 times x minus a squared. And then I still have the e term there. To find inflection points, you figure out where this is 0. Yeah, yikes. Well, factor as much as possible. There's a common factor of 2 in each term, and there's also a common factor of e to the -x minus a squared over b. What's left over? With this one, there's a -1 left over. With this term, there's a 2 left over and x minus a quantity squared left over. Right? If you want to double check it, you can multiply back through with the distributive property. And it does check. Nope, excuse me, I made a mistake. No, that's right. That's right. Never mind. To find inflection points, possible inflection points, set that equal to 0 and solve for x. This is never 0. So the only way this product of two things can be 0 is if this entire big thing is 0. And while you could expand that out and try to use the quadratic formula, you don't need to, because you can rearrange it like this and then like this. You know what? I made a mistake here. I did make a mistake. Way back up here. Yeah. I forgot about the b. Here, I had it here, but then I forgot about it. The b is there. Divide by b. And it also needs to be in these spots as well. So let's see here. It would be a divide by b here. And there'd be a b squared here. And I could factor it, let's see. I could factor out one factor of b, but I'd still have another factor of b right there. Hopefully I'm not making a mistake. Looks like I get a b over 2 there. Let me double check it. So I had the b there, it needed to be there, yep. Okay. Which means when I differentiate the first function here, the coefficient of x will be negative 2x over b, or 2 over b, so it's got to be there as well. I got a squared here. Factor out one factor. Yeah, I think that's right. So now take the plus or minus square root of both sides. You only need the plus or minus on the right side. It looks like x is a plus or minus square root of b over 2. Are the possible inflection points. Are they actual inflection points? Turns out they are. I think to verify that would be too much work. I mean, you can think about the sign of the second derivative changing here as x increases through these. It's a bit complicated to think about. These are inflection points. And so what you can say to summarize everything is that for a general a and b, the graph is centered on a, and your inflection points right about there and right about there. This one is a plus square root of b over 2, and this one is a minus square root of b over 2. So changing a translates the graph back and forth. Changing b, increasing b, say, affects how far apart these inflection points are. Let's make this more real by having Mathematica do it. I'll go ahead and use subscripts. So I'll use the palette here and make a subscript, f sub a b of x. And yeah, that's okay to do. I'm not sure how my memory is doing here, so I better clear f just to make sure there's nothing in memory that's going to goof this up here. In Mathematica, e is a capital E, so I get capital E raised to the negative x minus a squared over b. Once I have entered the function, I don't need the underscores anymore. So if I, for example, want to solve for where f prime sub a comma b, oops, I think I need the subscripts first. F sub a b prime of x equals 0. It must think A. Let's try clearing A and B as well. There we go. There's your critical point. That's going to be a maximum. Let's try for the second derivative. The inflection points, there they are. Is it the same as my answers? It doesn't look like it at first, but actually it probably is in disguise. Yeah, if you 2a divided by 2 is just an a. Comparing with these things here. And square root of 2 times square root of b over 2 is the same as square root of b over 2, it turns out, because square root of 2 over 2 is the same as 1 over square root of 2. Here's the reason. So I got the right answers, is what I'm trying to say here. And now if we make a manipulate and plot this function, f sub a comma b of x, and let a and b change. Say a starts at 0 and goes up to 2, and b starts at 0.1 and goes up to 2. I can't let b equal 0 because I'd be dividing by 0 in the formula for b of x right there. I'd be dividing by 0. There's the graph. When a is 0 and b is 0.1. As I increase a, the graph is a horizontal translation to the right. If I increase b, the graph gets more spread out. Okay. These things are bell-shaped curves. They're not exactly normal distributions from statistics because they're not scaled correctly, but they're very much related to normal distributions from statistics. And by the way, I'm bringing this up not only because it's important in statistics, but because we're also going to talk about it in chapter 5 on integrals, which is our last chapter, our last main chapter of the semester, which will be starting this week. Can I clarify anything? Please let me know if I can. That took longer than I was expecting, than I was hoping. I was also going to look at problem number 22, but I think that'll take too much time. I think it would be best if we now do some related rates problems. So I gave you a few problems on related rates. I think they were from this group of problems here about rectangles and triangles that are changing over time. Let's do another problem that maybe is a little more real life focused. Let's take a look at number 33. It's not a very pretty picture. It's a ruptured oil tanker, but you know, that does happen. Oil tankers do get ruptured sometimes, and then oil slicks do spread out on the surface of the ocean. And evidently this is spreading out in kind of a simple way. It's in real life, this probably wouldn't happen in such a simple way. We're assuming the oil slick is circular. In real life, it probably would not be circular because of the currents. And it's expanding. When the radius is 150 meters, the radius is increasing, expanding by a certain rate of 0.1 meters per minute. And its thickness is 0.02 meters. Questions are, how fast is the area of the slick expanding? And B, the circular slick has the same thickness everywhere and the volume remains fixed. How fast is the thickness changing? In this case, decreasing. So you got to get your mind around this. So you got to imagine. Imagination is important in math. What's going on? You got to pretend this is the water here, and you got the oil tanker sitting in the water. I'm not going to draw an oil tanker. But the oil slick is expanding. This is section 4.6, number 33. It's circular. Pretend it's a perfect circle. So this is the oil. So it's expanding. In part A, I don't think we need to focus on the thickness of the slick. Of course, if you need to imagine this would have a tiny amount of thickness to it. It's not just like one atom thick on the surface of the water. Imagine zooming in on this in this direction, there would be a certain small thickness to the slick. But I think in part A, we might be able to ignore that. So again, what does it say? Let's write down this information. When the radius is 150 meters, the radius is expanding by 0.1 meters per minute. Let's just focus on that first. Write that information down. When r, the radius, is 150 meters, the radius is expanding by 0.1 meters per minute. What does that mean with calculus symbols? It means the derivative of r with respect to t is 0.1 meters per minute. dr dt equals 0.1 meters per minute. That's how fast the radius is changing. And would mean, for example, that 1 minute later, the radius would be about 150.1. And a second minute later, it would be about 150.2. And a third minute later, it would be about 150.3. Those would be linear approximations. Now, is it going to be exactly those radii? Not necessarily, because r might not be a straight line. It might not be a linear function of t. It might be, but it might not be. So this is very much a derivative at a point. Better notationally would be to write dr dt evaluated at, well, this is a little funny, r equals 150 equals 0.1 meters per minute. It's a little funny because usually we put the time there, the independent variable. Now I'm putting the value of the dependent variable there instead of the independent variable. So it's a little funny, but it's still emphasizing that it's not just any old derivative that equals 0.1, but the derivative when r is exactly 150. The derivative at some other value of r could be something different. This is not necessarily a linear function. What's the goal again? Part A, how fast is the area expanding at that moment in time? What is dA dt evaluated at r equals 150? That looks funny as well because you don't see any r's there. What I mean here is find the rate of change of area with respect to time at the moment in time when r does happen to equal 150. Now, you don't know exactly what moment in time that is. You don't have a formula for r as a function of t. Doesn't matter. You can still write this kind of thing. You can still solve the problem, it turns out. That's the question. How? How in the world, if you don't have formulas, can you solve this problem? You can use the relationship between A and R, the area of a circle in terms of its radius. That's one thing you can do. This subject is called related rates. Okay, so this is a relationship. We know A equals pi r squared. If the oil slick is circular and the radius is r, the area is going to be pi r squared. And that's true even though the circle is getting bigger. This is always true for all t, for all time t. Even though you don't see a t in there, you need to imagine it being in there. I can't emphasize enough how much imagination is key to getting this. You need to imagine the slick getting bigger over time. But since it's circular, since we're assuming it's circular, this relationship still holds for all time. A and r do depend on time. I could write A of t equals pi times r of t squared. And that, in fact, might even be better to write. Though it's not so traditional to write. It's more traditional just to go ahead and this and not bother writing the t's, just remembering that this depends on t. Now get the rates into play. Differentiate both sides of that equation with respect to t, keeping in mind that both a and r depend on t. Pi doesn't, but a and r do. Well, the derivative of a with respect to t is not 0, not 1, it's dA dt. This kind of has somewhat of a similar feel as implicit differentiation. It's not the same thing, it's just somewhat similar in feel. With implicit differentiation, you might remember you had kind of complicated equations for x and y that you could not solve for y, and you differentiated both sides with respect to x, pretending y was a function of x, assuming that. This is not quite the exact same thing. I'm not differentiating both sides with respect to r here, for example. I'm assuming both sides depend on t and differentiating with respect to t. The derivative of this is not 0. It's not 2 pi r. It's 2 pi r times dr dt. The chain rule has to be used because r depends on t. R is like the inside function. If you think about it this way, differentiate that with respect to t, because I'm showing the t in here, it's more clear that it depends on t, and I would get 2 pi r of t to the first power times r prime of t. Right? You needed to know that kind of thing for the last test to be able to do that kind of thing. I'm doing the same thing here, it's just with Leibniz notation instead of the prime notation. This is a first power here, by the way, and this is a prime there. Same idea. These are the equivalent equations. I could write a prime of t equals that. That's a prime there. Same equations, just different notation. All right, well, how's this helpful? Now I can plug the numbers in. When r is 150 meters, dr dt is 0.1. I want to find dA dt when r is 150. Just replace r with 150 and dr dt with 0.1 and you're done. So when r equals 150, dA dt is 2 pi r, 2 pi times 150 times dr dt 0.1. That product is 15. Looks like this simplifies to 30 pi. Thirty times pi, it's about 94.25 units. Area, the length is in meters, so the area's got to be in square meters. Square meters per minute. So even though the rate at which the radius is increasing is very small, because the circle is already so big, the area is increasing at a pretty fast rate, it seems. numerically speaking. This is a much bigger number than that number. But it does look right. It doesn't look like I made a mistake here. It's a 15, by the way, that I was saying was equal to this product. Okay, can I clarify anything? Really, really fundamental kind of application of calculus. And you'll see this kind of thing come up in other contexts in science, engineering courses, physics, chemistry, what have you, where there are quantities that depend on time and they're related in some way. Like in chemistry, for example, you might have different chemicals in a reaction that have different concentrations that are changing over time, but maybe they're related because of some other law that relates them. And yeah, related rates would be a way to relate how fast they're changing. That's part A. What about part B? In part B, we're assuming the oil does have some thickness to it. Now you could say we're assuming that in part A as well, but we kind of just ignored it. It's got the same thickness. Now, that's probably not realistic to say it's got the same thickness everywhere. It probably thins out near the extremes, but for simplicity, assume it's the same. Then the volume remains fixed. So this fixed amount of oil has spilled. So it's still expanding. The circle is getting bigger, but it's the same amount of oil. So the thickness has to be getting smaller if it's the same amount of oil. And so the question is, how fast is it decreasing? And since they're saying how fast is it decreasing, with the word emphasis on the word decreasing, they actually probably want a positive rate of change here. How fast is it decreasing? But the derivative of the volume with respect to t itself would be a negative quantity. Excuse me, no, dv dt would be 0. The derivative of the thickness would be negative with respect to time. So what we're really after here in B is we're now assuming the oil has some thickness to it. We're really assuming it's a very large pancake shape. Okay. With a certain radius, a certain thickness, I'll call the thickness h because it's a height. And we want to find really the absolute value of dH dt to say how fast it's decreasing. Since they say it's decreasing, they're after actually a positive answer. At the same moment in time when R is 150 and dr dt is 0.1. Any ideas? You can pipe in if you got an idea. Staying awake with me here? I know it's maybe even harder to stay awake now when you can't be in class. I don't know. It's getting to nap time in the afternoon. We got to bring the volume into play. This pancake shape is a cylinder shape. It's a flattened out version of a can. The formula for the volume of a cylinder is pi r squared h. So we got to use that somehow. Well, you can still do the same thing as before. Differentiate both sides with respect to t. Everything depends on t. Well, actually the v doesn't. Sorry about my mom coming in here. V, they were told, stays constant, right? Because it's a fixed amount of oil. dv dt will be 0, and that must be key to solving the problem, actually. That must be important. I mean, if I differentiate both sides with respect to t initially, d dt means differentiate both sides with respect to t. I'm going to get dv dt on the left side, but I know this is 0. That's given. It's 0 for all t. V is a constant. What about differentiating the right side? Pi is a constant, but both of these are not constant. As R increases, as the oil slick gets bigger in radius, H has got to decrease. It's got to get thinner if it's the same amount of oil. They both depend on time. I need the product rule here. The derivative of the first function, pi r squared, would be 2 pi r dr dt, chain rule, times the second function. That is the derivative of the first. If you like, you can pretend it's pi r of t quantity squared. Bring down the 2 pi r of t to the first times r prime. That's what I've got there, just with the Leibniz notation. Times the second function plus the first function times the derivative of the second, dh dt. And again, it doesn't matter that I don't have formulas for r and h as functions of t. I still have information about what r and dr dt are, and that'll be enough to help me solve the problem. I want to find the absolute value of dh dt. I better find dh dt itself first. Solve this equation for dh dt. It's an algebra equation now. Just subtract this thing from both sides. I'd get negative 2 pi r h dr dt equals pi r squared dh dt after subtracting this from both sides. And then divide both sides by pi r squared. The pi's will cancel. That's nice. And one factor of r will cancel. I'll get a negative 2h dr dt over r. Just divide both sides by pi r squared. If I divide this by pi r squared, the pi's cancel. One factor of r cancels. I'm left with a negative 2h and a dr dt in the top, and just an r that didn't cancel in the bottom. Now I can plug in numbers. I can plug in r equals 150. I can plug in dr dt equals 0.1. What should I plug in for h? The one piece of information we have not used. That at this moment in time, h is 0.02 meters. So using h equals 0.02 and all these other things, I'm going to get dh dt is negative 2 times 0.02 times 0.1, all divided by 150. It's going to be a number very close to 0. Two times 0.02 times 0.1 divided by 150, and then put a minus sign in there. Negative 0.000267 around. Don't forget the negative sign. Negative 2.67 times 10 to the negative 5. This would be in meters per minute. That's the rate of change of h with respect to t. Then to find out how fast the thickness is decreasing, take the absolute value sign of that, get rid of the negative sign. The final answer would be the same thing without the negative sign. A number very close to 0, which should make intuitive sense. I mean, this is a tiny thickness to begin with. It should make sense that it's changing in a rate very close to 0. Okay, are you with me here? Final answer, you get rid of that negative sign because the problem is phrased as how fast is it decreasing. If it was phrased as how fast is it changing, then you'd want to say include the negative sign. But it's already saying that it's decreasing, and so you take the absolute value of that. But you only need to do the absolute value at the very end. By the way, a common mistake people make in all this is plugging numbers in too soon, like thinking they should plug numbers into here, for example. No, don't do that. You've got to differentiate first before you plug any numbers in. That's really essential to make sure you only plug numbers in after you've differentiated. Any clarification I can make there? In our last few minutes, let me just give you some hints about a couple other examples. I'll assign at least a few of these. Like number 44 here, or one of those dreaded train problems. A train is traveling at 0.8 kilometers per minute along a straight track, like in this picture. A movie camera 0.5 miles away is following the train. Part A, express z as a function of x. Hey, that's a right triangle, use the Pythagorean theorem. Part B, how fast is the distance from the camera changing when the train is 1 kilometer from the camera, I guess when z is 1. And C, how fast is the camera rotating? Interesting. So a couple key things to think about here. So Pythagorean theorem, it's a right triangle, so we can use the Pythagorean theorem. We could say, for example, z squared, square the hypotenuse, is x squared plus 0.5 squared. And that can then solve, you can take the square root to solve for z in terms of x. And I guess I've essentially done part A for you there. Part B, how fast is the distance changing? What is dz dt? How fast is the distance changing when z is 1? Sounds weird to say that. Find dz dt when z is 1. What I said just 2 minutes ago is really important. Don't plug in 1 for z right away. Only do it at the end. As far as dz dt, actually we can avoid the square root. We can just differentiate both sides of this equation with respect to t and get 2z dz dt equals 2x dx dt plus 0. We can solve that equation for dz dt. dz dt, divide both sides by 2z, would be x over z times dx dt. That would be the equation to solve for part B, but only plug in z equals 1 after you've differentiated like this. You'd also have to figure out x and use the fact that dx dt is 0.8 kilometers per minute. The train is moving to the right here, so x is increasing at a rate of 0.8 kilometers per minute. For part C, we're talking about how fast a camera is rotating in radians per minute. We need to bring an angle into play. This angle here. And as the train moves further and further away, this angle gets bigger and bigger. The triangle looks more and more like that as the train moves. The angle gets bigger. So you need to relate theta to z and x, or maybe just one of them. And in fact, it's probably easiest just to relate it to x. SOHCAHTOA, that's the opposite side. This is the adjacent side. Probably want to use the fact that the tangent of theta is x over 0.5.
Luke, guess who's getting that bat? Or are you sleeping?
Question?
Guess who's getting that bat today? Kirilov. He's in the lineup.
I'm not sure who.
My bad.
Okay.
I woke up Luke by accident.
Differentiate with respect to t, you're going to get secant squared theta d theta dt equals
No, this is Luke actually.
dx dt over 0.5.
Oh,
And solve that for d theta dt.
yeah.
Is that a private conversation you're trying to carry on? Okay. So sometimes you have to use Pythagorean theorem or trigonometry to solve a problem. Any questions? Use knowledge that you have learned in the past. You may have forgotten. Look things up if you need to. We'll see you on Wednesday.